introduction that the future of the field is in the experiment. We have a session which is the last one, full of experimentalists. And the first speaker is Seongshik Oh from Rutgers. And he will be talking about thin film topological insulators and interface engineering. As well.
Yeah, I'm really happy. This is the first time in Taiwan. Yes, this is the first time in Taiwan, and this is actually the first time outside Korea in East Asia for me. Actually, this is the first place outside Korea in East Asia, and especially I want to thank Professor Rainey, but she's not here, and the other organizers. So I had also very wonderful excursion yesterday. It was really great. Okay, the 101, the Taipei 101 was really great. Okay, so today I am so far there was only one experimental talk by Professor Saito, and he's gone. Oh, okay. Now, it seems like this is the only session that is full of experimental talks. So we are more now on real things. Okay, now this session. So I want to start with this. I want to really discuss something real, and so it'll be a the Professor Saito also talked about something real as well, but something really real. Okay, so. But yes, the topological insulator, yes, topologist does not sound like so real, but we'll see how much is real and how much is not. So I'll start with something not related to topological insulators first. So it is okay, everybody knows Nobel Prize. So let's see what, as you know, in 2009, it's 6 years ago. It is 6 years ago. So the Nobel Prize was 6 years ago was given to Professor Kao. I'm not sure where he is at the moment, but so it is okay. If you look at the website of the short press, the report, it says for groundbreaking achievements concerning the transmission of light in fibers for optical communication. Basically, okay, as you know, all our internet is impossible without the fiber. The fiber optic invention. So he was the key inventor of this. But probably okay. Does anyone know what is the key idea behind what is the key concept or key contribution Professor Kao has made? Why did he win? What is it exactly that he invented to win this Nobel Prize? Does anyone know? Nobody knows? Okay. So he is said to have made this major groundbreaking achievement. Let's go further. What is that exactly? This is it. So let's see. So what he did is Dr. Kao basically realized that impurity of glass material is the main cause to prevent the optical fiber, the fibers, the glass to be used as communication. And the important thing is the reason the light cannot propagate long distance through glass. He calculated that he found that he realized that it is due to impurities, and that impurities he believed that it could be removed because that impurities it's not a fundamental impurity. It was actually mostly some water-based some impurities, so it could be removed. And eventually, if that happens, it could replace copper. Copper was the material that was used to transmit the telephones up until 1960s. So they used copper, but the very fact that the optical fiber can maintain, if you can remove these impurities, can propagate much longer, hundreds of times longer distance than copper wires can do. Once Dr. Kao sort of showed that, at that time, yes, people didn't believe. Okay, they didn't believe. But later on, after he showed that, and after the other people, after he convinced people to make those fibers following his ideas, after it was demonstrated, it revolutionized the whole communication, as you know, as we all know. So that was actually impurities. So that's one event why what the impurity was so important. Impurity could lead to Nobel Prize. Okay. That's one incident. Another one, the more recent one last year, the Nobel Prize in Physics. Probably you know more about this. It is for the invention of efficient blue light emitting diodes, which has enabled bright and energy saving white light sources. So these three people, these Japanese these scholars, these three people have invented this blue. Okay, blue LEDs. Again, okay, what was the key? What is the key? Let's see. The key, people have been working on this for decades. The key is actually this, how to dope gallium nitride. That was the key. Basically, because the main problem is gallium nitride was predicted to provide blue LED already in early 1960s, but people were not able to make gallium nitride into any diodes because they were not able to dope, they were not able to p-dope gallium nitride. So when this professor Akasaki and Amano demonstrated that it could be doped by zinc somehow, and then it was really further clarified by Professor Nakamura that it could be really done reliably. The p-doping could be done reliably, and then now it has become possible to make blue LED, and that's why we have all the light type being replaced by now LEDs. Okay, so as you can see, these two are examples of what really is important. And okay, there's this famous saying, probably most of you know this famous saying, the devil is in the detail. But for this specific case, it is in the defect. So that's very important. If you look through just go through the contents of the Nobel Prizes, many of the things are actually related to controlling and eliminating defects. So it is actually, it may look a little mundane for some high-flying theorists in some cases, but in fact, that leads to many breakthroughs occur through proper defect understanding and control. So, based on that background, I will now go over what I'm going to talk about related to topological insulators. So, I will first briefly introduce topological insulators, and then one of the famous problems in topological insulators, which is bulk conduction problem, and then we in fact we can actually solve this problem using thin film engineering, and that can also lead to, by solving the problem, it can also lead to quantum Hall effect. And then also as another side aspect of topological insulator is you can also make topological insulator phase transition, and again we have some finite size effect which is usually not well treated in theories, and also how disorder can also break the topological protection. So that's I'll go over those in turns. So the first one, okay, what is topological insulators? Okay, topology. Most people know what topology basically means. So this ball versus the cup. Yes, there's one hole, and it doesn't have any hole. So their topology is different. It's very simple. But that's real space topology. Okay, it's easy to see. But the K-space, the topological insulator is based on K-space topology. So if you look at the so-called topological insulator, one of the most popular materials we know of, which is bismuth selenide. If you look at bismuth selenide versus another, the regular normal insulator like diamond, they don't look much different. Topology looks the same, right? So they don't look any different. So what is different? It is actually the band structure topology that is different. So at least from real physical property point of view, the difference actually comes from its transport properties. So let's say if you have if you measure the transport properties or resistance of regular insulator, then everything is insulating, so current does not flow through any places. But topologic insulator, for some reason, we'll go over pretty soon, is the current flows only through the surfaces, but not in the bulk. At least that's how it is supposed to be. So inside is insulating, but the surface is metallic here, but surface is insulating on regular material. You don't really get a little bit better view of what's really happening. A simple view is like this. This is a very simple view. So let's say this is vacuum or air. Then you have a band structure, the conduction band, valence band, outside the same. So if this is not, let's say you start from bismuth selenide, imagine the bismuth selenide does not have any spin-orbit coupling strength. Then, okay, it is insulated, there's nothing happens, so then they basically have the same, there's no surface state or anything happening. But as you increase the spin-orbit coupling strength, what happens is the band gap of this imaginary bismuth selenide now, the band gap decreases. If you further increase, at a certain point, it gets inverted. The band inverted, then you can see that there is a crossing at the surface here. So you can see that if, let's say, Fermi level is anywhere inside, then you always have to cross this band. If the Fermi level crosses the band, then it is metal. So you are guaranteed to have metal here. So that's why now at this stage, this bismuth selenide has different topology in band structure topology relative to the vacuum. So you have the surface state, which is supposed to be guaranteed against any non-magnetic disorders. That is at least what is theoretically predicted and theoretically confirmed and experimentally confirmed by probes like angle resolved photon emission spectroscopy. The surface bands. Okay, you have surface bands, continuous surface bands, and so okay, this was the proof of presence of surface state as predicted by theories. So, okay, bismuth selenide. I said that bismuth selenide is the one of the most famous topologic insulators, and the structure is layered structure. So bismuth selenide is composed of 5 layers of these atomic layers. So bismuth to selenium 3, and then between those layers there's a van der Waals bonding. So this minimum unit is called quintuple layer. That is the minimum unit. So yes, this quintuple layer usually is the acronym for quintuple layer is QL. So that is commonly used. So that's a layer structure, and from the top view it has a 3-fold symmetry, or roughly 6-fold, but the exact symmetry is 3-fold symmetry. So that's the famous topologic insulator material. Now, okay, that is so far it was the ideal situation. But there is a problem. The problem is we know that the metal. What is metal and what is insulator? Well, metal is if you have a Fermi level crossing the state, the band, then that's metal. But if you don't have any state where the Fermi level crosses, then that's insulator. That's what metal and insulator is at 0 temperature. But the reason topologic insulator is because it has this surface band which originates from this different topology of the material itself, this surface state. But if your Fermi level ideally should be at this Dirac point, and so if you view this as a bulk band, this is surface band, and then the surface band is in the gap of the bulk, so bulk is insulating. But the surface state is conducting because it crosses the surface band. So this is the ideal case. But when people have done the measurements using R-test, which is the most common probe, people have found out that sometimes, let's say, sometimes the R-test spectrum is like this, sometimes like this. So if you look at this is the bulk band. You see signatures of bulk band. Then this is the Fermi level, basically. This is Fermi level. Fermi level crosses the bulk. So, okay, bulk is metallic in this case. Okay, but in this case, oh, bulk is somewhere here, so you don't see the bulk crossing. So bulk is insulating. So people have concluded at this, around this time that, okay, we have achieved bulk insulating sample. That's what people believed at the beginning when those RPS people. But in fact, the reality is not that, because reality is, if it was like this, in fact, the inside there's a signal band bending, and inside it is okay metallic over here. Okay, it was metallic, but anyway, so it is not any surprise. But the surprise is, even in this case, people thought that the Fermi level is inside the gap, but inside the bulk, the Fermi level is still near the bottom, but still above the conduction band. So it was still metallic. So regardless of whatever you see in RPS, bulk was always metallic. So this was this turns out to be always the case. Then why do we have this bulk conduction problem? So let's say if it is in real ideal materials, then the ideal material will not have any defects. Then the Fermi level is at the drop point. Okay, then bulk is insulating, surface is metallic. But the problem is, in real materials, you have all these defects. In particular, because of the van der Waals bonding between the layers, the bonding energy between bismuth and selenium is pretty weak, and also especially at this van der Waals bonding, the bonding is so weak that you can easily have a little selenium vacancies. Then if you have selenium vacancies, that contributes n-type, that behaves as n-type dopants. So the Fermi level goes up, so it becomes metallic. So, okay, as I said, it is because of the selenium vacancies. That's why the bulk is always metallic. Can we get better understanding of exactly why? Then there's this famous plot, so-called Mott criteria. There's quite famous criteria which is probably made in 1960s or something like that. And then the concept, what it means is, if your density of defect density or doping density, if doping density is larger than some critical value, this is the critical value. If the doping density is larger than critical value, then if it's larger than that, then they behave as metal. So that means if you cool it down to zero temperature, they remain as metallic. But if the doping density is below the critical value can be calculated if it's actually determined by the so-called effective hydrogen Bohr radius of that particular material. But each material, you can calculate the effective Bohr radius of the material using the effective dielectric constant and plug in an effective mass. By plugging in those numbers, you can calculate the effective Bohr radius for all the materials, and then this line comes from that. Line corresponds to this. Then it turns out that as you can see, almost all materials, the critical carrier concentration, or doping concentration, that leads to this metal insulation turns out to be quite universal. So if the doping density of, for example, silicon, let's take silicon as an example. Silicon is the most widely known. So silicon, if your doping density is below, let's say, below 10 to the 18 per cubic centimeter, then the carriers freeze as you cool down. So they are conducting at room temperature, but if you cool it down, then they all freeze. So at low temperature, they are all insulated, completely insulated. If your doping density is lower than this critical density. That's why all these our semiconductor or chips, their doping density is usually below this 10 to the 18. So if you cool these down, they don't work because all the carriers freeze. They work only down to maybe minus 10 degrees Celsius or something like that. Because the carriers freeze, they behave as insulators. So they all insulate. But if your doping density of, let's say, for silicon is higher than 10 to the 18, let's say 10 to the 19 or 10 to the 20, then they remain metallic all the way down to zero temperature. Usually it's called degenerate semiconductor, that they remain as metallic all the way down to zero temperature. If you do the same if you did that kind of calculation for a very simple calculation for bismuth selenide, it turns out that if you plug in the numbers, the dielectric constant and effective mass, then this critical carrier density turns out to be something like 10 to the 14 per cubic centimeter, which is 4 orders of magnitude lower than that of the silicon. It's right over here. So what this means? It means that your dope or your defect density should be lower than 10 to the 14 to have this bismuth selenide system in insulating state in their bulk. Otherwise, if your defect density is larger than 10 to the 14, then they will remain metallic. So let's say if you compare all the literature values available, then that's sort of you can see that the carrier densities are all 10 to the 16 around that. So this is the 10 to the 14 line. So only if your carrier density is below 10 to the 14, you really achieve this Mott criteria-based insulator. Otherwise, it's always basically metallic. But there's another method to make them insulating. This is the approach all the people are currently using. So you probably hear every now and then many people say that they have achieved insulating, twin insulators. In fact, what they did is not really this way, but what they did is they made the film sort of disordered. If you make the film disordered, then there's another criteria which is called Ioffe-Regal criteria. What that means is if this film gets disordered, then the mean free path decreases. Then eventually, even if it was metal, they all localized. But that insulator, this is insulator. If the mobility drops, then it all becomes insulating at low temperature as you cool it down. But this is quite dirty state. So highly disordered, dirty. So it behaves insulating, but it is not really nicely exponentially. The resistance does not nicely exponentially increase with like this regular strong insulator. So, but this is where people call that where these bulk insulating samples are actually. So so you can see that this native defect problem is quite fundamental. So how can we beat this? It's fundamentally somehow these materials have native defects. You cannot beat it. So okay, we are doomed. Okay, yes. Maybe, but there always is hope. It turns out that there's actually maybe this probably is not the only way, but one way is using this thin film. By making films thin, there's actually it turns out that you can really overcome this problem. The way it works is, let's say somehow you manage to make the surface, as I said earlier, the surface could be on the surface you can have downward band bending or upward band bending. But let's say you are able to achieve upward band bending, then as we know, the inside the material, it is all metallic. This is Fermi level, but at the surface you have upward band bending, let's say. Now, you make the sample thin. Then, if you make it very thin, then, okay, at a certain point, the depletion, if you make them thinner than depletion length, then you're energetically, you cannot bend this, the band bending cannot maintain beyond certain level, so then Fermi level should pop down and it will become insulating. But the problem is, all the bismuth selenide materials, we know that it turns out that they have this downward band bending. So this is downward band bending. So upward band bending, okay, conceptually, you can probably then, if you achieve upward band bending, then you can make the sample insulating. But it turns out that whenever you make bismuth selenide, you always have downward band bending. So okay, again, there's a problem here. Okay, then let's take a look a little bit more. Exactly how we achieve downward or upward band bending. So if you check there's a surface band, and you know roughly where the bulk band is, and all these levels you know, And then it turns out that if your carrier density, the total sheet carrier density is exactly 10 to the 13, or 10 to the 13, this 10 to the 13 per square centimeter, then you have the bottom of the convection band matches, is flat. You have actually flat band. But if your total sheet carrier density is lower than, higher than this value, 10 to 13, then you have accumulation layer. If your total carrier density is lower than this value, you get the downward bending. So this is what we want. We want carrier density lower than 10 to the 13. That's the criteria. So again, in RPES, from RPES, if you look at the same thing from RPES. So this is 10 to the 13 carrier density. If carrier density is higher than 10 to the 13, then you have your bulk is metallic. You have formula that crosses your band, your bulk, so you have downward band bending. That's not good. But if your formula level, if your carrier density is lower than 10 to the 13, then you have upward band bending, and you can now, by making the samples thin, you can, in principle, achieve the bulk insulating sample. So roughly, this is basically repeating the same thing. So when the film is thick, yes, you have depletion layer. So basically, you have to first achieve carrier density lower than 10 to 13. Then, if your film is thick, then it is still metallic because your bulk is still metallic. The bulk, you can never beat the math criteria. So bulk is always metallic if the sample is thick. But if you make it thin, then at a certain point, you can no longer, the formula level can no longer be above the conduction band. So bulk becomes insulating if you make your film thin. So basically, if you make a low carrier density sample somehow, and if you make it thin, then bulk will be automatically insulated. There could be more complication, but at least to the simplest level, this can happen. So as we saw, the thin film has a hole. How do we make it? The tool we are using is molecular beam epitaxy, and it's very simple conceptually. You just this is thermal heat. It's like you just heat your water, then water evaporates. So it's like that. You heat whatever the element, for example, bismuth and selenium. You heat bismuth evaporates. You heat selenium evaporates in a very good vacuum. Then you form bismuth selenide on your substrate. And so especially for this kind of situation, MBE, there are other thin film growth schemes, but there is some advantage of using MBE because you can control a couple of things to your advantage. So the first thing is, compared to bulk growth, your growth temperature is much lower than the bulk growth temperature. Typically, the bulk growth temperature should be done at the melting temperature, but because you are growing really slow rate in thin film form, your growth temperature can be much lower than the melting temperature. Why this is good? Because the defect density is thermodynamically it is determined. So if it is formed at high temperature, thermodynamically you have to have many defects. If it is grown at low temperature, you have fewer defects. So you can in principle achieve fewer defects by growing them at much lower temperature. That's to your advantage. Another thing is you can again, because we know that it is due to selenium vacancies, so if you grow them you can grow this material in high selenium rich condition. So 10 times, 20 times, 30 times more selenium conditions. Then this is beneficial to achieve to minimize selenium vacancies. So both help. And but also this in MD, another important tool is this reflection high energy electron diffraction. That's a very important tool because that helps you to, you shine high energy electron beam at a glancing angle and you look at the read pattern. This is the diffraction pattern. By looking at the diffraction pattern, you can understand how films grow. So you can real time, you can monitor the film and you can judge right away how your film grows. Because otherwise, if you do not know, usually in other methods, you just grow it blindly and you characterize the films after you finish the growth. So it takes a really long time to find out if something went wrong. But in in MBE because of read. You can tell right away, you can fix it. So that's another good advantage. So depending on the morphology, your read pattern can be characteristic. You can have characteristics of patterns. So you can sort of view in your brain that you can roughly guess what the real space morphology would be like. Also, that read provides atomic layer control because of some oscillations. One oscillation corresponds to one molecular layer, so that provides another control. So this is our MBE system we use. So then what is the status of bismuth cell and thin films? Okay, the MBE has advantage, but that does not solve the problem. Because if you grow it, there's this intrinsic some advantage of MBE films relative to other growth method. But even with that, there are still many problems. So let's see what the status is. So the bulk defect density, if you grow thin films, is 10 to the 17 to 10 to the 19 per cubic centimeter. But it turns out that you have surface defect density, which is orders of 10 to the 13 per cubic square centimeter, which is equivalent to roughly 10 to the 20 cubic centimeter if you assume that all the defects are confined to just one monolayer. So if you compare this, surface defect density is much bigger than bulk defect density. So earlier I mentioned that our target carrier density is 10 to the 13. This is our target value. So carrier density should be below 10 to the 13 in order to have any hope of making them bulk insulating. As you can see, on any substrate, on silicon, aluminum oxide, people have tried this and that. You always have more than 10 to the 13 carriers. So your surface, so your bulk is actually always metallic. So this line is so difficult to achieve. So difficult to go below this. That was target value. If imagine that, but if you can lower the defect density of surface defect density, if your surface defect density is equivalent, similar to the bulk defect density, let's see if that is possible, then in principle you can achieve quite low surface, something like 10 to 11. If you can achieve even down to 10 to something like 11 square centimeter, even for something like 10 nanometer thick film. So if you can suppress the surface defect density to the level of bulk, then your total carrier density could be way, way lower here. So basically, the surface defect density is really currently dominating. So just to overview this one more time. So here I'm showing various substrates, and the films grown on various substrates: aluminum oxide, silicon, indium phosphide. They are some of the most popular substrates. Okay, so you can see that regardless of this bulk defect density, your surface defect density is always higher than 10 to the 13. So whatever you do, you can never